Welcome back to The Explainer. Today, we're diving into something that literally challenges the foundational code of reality. For centuries, we've had a very specific, rigid language to decode the universe's secrets. But what if that language, the absolute bedrock of all our logic, is actually due for a massive, massive upgrade? So let's jump right in. When you think of math, your brain probably goes straight to numbers, right? 1, 2, 3. Rigid, distinct little units. Well, I want to completely challenge that basic assumption today. What if the deepest foundations of mathematics weren't actually built on discrete numbers at all, but on continuous, flowing shapes? I know it sounds a bit like science fiction, but this is a real, massive paradigm shift happening right now in advanced mathematics. To really wrap our heads around this, we have to look at the old guard versus the new frontier. For over a century, the absolute foundation of math has been something called set theory, specifically Zermelo-Fraenkel's set theory. Think of a set as a rigid container holding completely distinct objects, very discrete. But now enter the challenger, homotopy type theory, or HOT for short. Instead of those rigid little containers, HOT treats mathematical objects as continuous, fluid geometry. It's a total shift from absolute rigidity to dynamic spatial relationships. Now, fractal geometry brilliantly captures this idea of continuous spaces. Think about mapping the behavior of orbits in the Mandelbrot and Julia sets. You aren't just getting isolated points, you get this infinitely complex, interconnected boundary. In these mathematical spaces, you don't just, hop from one number to the next, you actually flow continuously through an entire topological landscape. Which brings us perfectly to the formal definition of our main topic today. Homotopy type theory is a mathematical foundation where objects are treated as spaces that can be continuously deformed. If you've ever heard that old topology joke about a mathematician not being able to tell the difference between a donut and a coffee cup, well, that's exactly what we're talking about here. Because a donut made of clay can be smoothly squished and stretched into a coffee cup shape without tearing the clay, they are fundamentally equivalent spaces. HOT takes that intuitive, visual geometry and literally turns it into the rigorous foundation for all of math. Section 1. From sets to spaces. A paradigm shift. So traditional math, the stuff built on that Zermelo-Fraenkel set theory, actually ran into a massive historical crisis back in the 20th century. A brilliant logician named Kurt Gödel proved his famous incompleteness theorems. He mathematically proved that any formal system capable of basic arithmetic is inherently limited. You just can't have a system that is simultaneously complete, consistent, and effectively axiomatized. Basically, Gödel showed that there will always be true statements in mathematics that are impossible to prove using the rigid rules of that exact system. It created this huge crisis of unprovable statements. Set theory hit a logical wall. We desperately needed a new foundation that could reliably verify mathematical truths without falling into those same traps. And what's incredibly cool is how homotopy type theory entirely sidesteps those rigid historical limitations. By completely abandoning rigid numbers and sets and instead treating mathematical objects as fluid spaces, continuously deforming from one state to another, we create a system that speaks the language of structural equivalence. We aren't just shifting symbols around on a chalkboard anymore, guys. We are describing how complex structures fluidly map onto one another. Section 2. Understanding path induction. This whole concept requires a grand new version of mathematical proof. It's called path induction. See, in traditional math, equality means two things are exactly identical. In HOT, we use path induction instead. It goes like this. Step 1, you identify your two spaces. Let's call them state A and state B. Step 2, you attempt to trace a continuous, unbroken mathematical path right between them. And step 3, if you can confirm that state A smoothly flows into state B without breaking, tearing, or poking any new holes, boom, you've proven them equal. So, the absolutely crucial takeaway here is that path induction completely redefines equality. Equality is no longer just identity. It's flow. It's a continuous path. If you can build a path between two mathematical concepts, they're equal. Now, I know this sounds incredibly abstract. You might be sitting there wondering, why on earth should anyone outside of an Ivy League math department care if an equation flows? Well, buckle up, because this abstract geometry is about to become a literal matter of life and death. Section 3. Verifying bug-free software. Homotopy type theory is, without a doubt, the ultimate bridge between theoretical geometry and practical computer science. Because of the unique way type theory is structured, a mathematical proof can actually be read almost identically to a computer program. When a mathematician writes a proof in HOT, A computer can read it, understand it, and automatically verify its complex logic. We are taking the flaw-prone human element totally out of checking code and replacing it with absolute mathematical certainty. Think about the real-world stakes here for a second. We rely on software for literally everything. We are talking about ensuring that the software inside self-driving cars navigating busy city streets or pacemakers and critical medical devices keeping people alive is 100% bug-free. A single human error in a traditional line of code can and has caused disasters. But if the software's logic is verified using the continuous paths of homotopy type theory, the computer mathematically guarantees that the code will execute perfectly, every single time without fail. It is basically the holy grail of software engineering. And the best part? This isn't just theoretical. This is happening right now. Mathematicians and computer scientists are actively using what are known as proof-assistant software programs, tools like ROC, which used to be called Kook and Isabelle. These systems use formalized logic to completely verify massive continuous mathematical proofs. Get this, a computer-verified proof of both of Gödel's incompleteness theorems was successfully run using Isabelle. We are literally using computers to check the math that proves the limits of traditional math, all to build significantly safer software for humanity. It's just this incredibly beautiful loop of logic.
Section 4. Join the mathematical frontier.
If these deep dives into the explainer expanded your mind even a little bit today, make sure you don't miss our next breakdown. We're decoding the universe one topic at a time. So hit that subscribe button right here on YouTube for weekly deep dives. If you really want to get into the weeds, follow our Substack for the full source documents and study guides. And of course, jump into our Discord to chat, theorize, and hang out with fellow math explorers. I want to leave you with one final lingering thought. We used to think math was just counting rocks. Then we realized it was a rigid structure of sets. Now we're discovering it's actually a fluid, continuous landscape of shapes flowing into shapes, verifying the very code that runs our modern lives. So I have to ask you, if the absolute foundation of all logic is just shapes continuously flowing into one another, what ultimate shape is our universe trying to decode? Think about that. Thanks for joining me on The Explainer, and I'll see you next time.